Welcome to our final segment on the Milky Way. In this segment, we'll go over our current understanding about the structure and size of the Milky Way as a whole and our place in it. We'll examine the galactic center with its supermassive black hole. We'll go a little deeper into the nature of a black hole. We'll explore the galactic disk with its spiral arms, and we'll cover the latest information on the galactic halo. And, as usual, we'll discuss how we came to know these things from our viewpoint deep inside the galaxy itself. On January 1st, 1990, from its orbit around the Earth, the Goddard Space Flight Center's Cosmic Background Explorer created this edge-on view of our Milky Way galaxy in infrared light. Here's a newer inside image of our galaxy. In fact, it's the most detailed map ever made. It was released in 2018 by Gaia, the European Space Agency spacecraft, that recorded the position and brightness of 1.7 billion stars, as well as the parallax, proper motion, and color of more than 1.3 billion stars. The map shows the density of stars in each portion of the sky. The galaxy has a center with a central bulge, a disk of rotating stars and dust, and a halo without dust clouds and peppered with globular star clusters. The disk is at least 100,000 light-years in diameter, and the halo is much larger than that. We'll go into each of these galaxy components, starting with the galactic center. We'll cover how images like these are created from inside the galaxy and how impossible it is to get an image from outside the galaxy later on in this segment. The world's great space observatories, the Hubble Space Telescope, the Spitzer Space Telescope, and the Chandra X-ray Observatory, have collaborated to produce this unprecedented look at the central region of our galaxy. Hubble documented vast arcs of gas heated by stellar winds from very large stars. Spitzer's infrared picked up the pervasive heat signals of all these stars. And Chandra detected X-ray sources from ultra-dense neutron stars and small black holes. Together they produced this spectacular image. The central object in the Milky Way is known as Sagittarius A star, or Sag-A star for short. It is surrounded by so many stars and gas and dust that it is almost impossible to see. Teams of astronomers and astrophysicists have been working on understanding Sagittarius A star for over 25 years. The UCLA Galactic Center Group, along with the Keck Observatory on top of the Mauna Kea volcano in Hawaii, and the European Southern Observatory and its array of very large telescopes in Chile, and the Max Planck Institute for Extraterrestrial Physics in Germany, and many others have made dramatic progress in advancing our understanding of this critically important part of our galaxy. After decades of careful observations, the speeds and orbits of around 45 stars around Sag-A star have been calculated. This enabled measuring the precise location of the point they are all orbiting around. The measured orbits also identified the gravitational pull from this point, which in turn gave us its mass at 4 million times the mass of our Sun. But when we look at this point, we don't see anything. This was strong evidence that Sag-A star was a black hole, because stars are known to be unstable at much smaller masses. The star S2 is of particular interest because it passes closer to Sag-A star than any other. It's a single main sequence star with 10 to 15 times the mass of our Sun. Observations of the star showed that its orbit took it to within 20 light hours of Sagittarius A star in 2002, without bumping into anything. That puts Sag A star's 4 million sun mass into a very small place. For many astrophysicists, this constituted proof that it was indeed a supermassive black hole. But others pointed out that an extremely dense dim star cluster could produce these results. But if Sag A star were a cluster, S2's orbit would wobble. It did not wobble. This was the final proof point. 500 years after Copernicus put the Sun at the center of our solar system, this team identified Sagittarius A star as a supermassive black hole at the center of our galaxy. But we weren't done with S2. Its orbital period is 16 years. Following the 2002 passing, a major effort was mounted to upgrade ESO's Very Large Telescope array to enable the precision needed to reveal the true geometry of space and time near this object and test Einstein's theory of general relativity. These new instruments followed S2 very closely. At the start of 2018, it was accelerating towards Sag A star, reaching relativistic speeds. On May 19th, it reached the closest approach, Pericenter. At that point, it was traveling at 7,650 kilometers per second, or 4,753 miles per second. That's almost 3% of the speed of light. Its distance from the black hole was just 18 billion kilometers, or 11 billion miles. That's only 120 times our distance from the Sun. The separation on the sky between the 2 points was just 15 milliarcseconds. It was also reddening in color, as the black hole's gravitational field stretched its light to longer wavelengths. The color change in this illustration is exaggerated for effect. The actual reddening is quite small and would not be visible to the naked eye. S2's velocity changes close to the black hole were in excellent agreement with the predictions of general relativity. In addition, the change in the light wavelength agreed precisely with what Einstein's theory predicted. But understanding what is happening this far away is always prone to errors. I remember when we thought there was a gas cloud, G2, that would be entering the black hole in 2014. This never materialized. In our current case, some astronomers point out that massive non-luminous objects, such as stellar mass black holes, might be present and could affect the orbital dynamics of S2. More research is needed to rule out this possibility. Here's a full dome illustration that shows how Sag A star might look to viewers on a planet orbiting S2 as it orbits the black hole. We'll cover black holes and why our supermassive black hole might look like this. But first, we'll cover how the ESO Very Large Telescope actually measured the minute distances associated with S2 and Sag A star, 26,000 light-years away. The Hubble Space Telescope can resolve angles on the sky as small as 50 milliarcseconds. The angular distance between S2 and Sag A star at pericenter was just 15 milliarcseconds. That's 42 billionths of 1 degree, and 3 times smaller than Hubble can resolve. To follow S2 as closely as they did, astronomers had to use a stellar interferometer. These kinds of telescopes can resolve images 30 to 40 times smaller than optical telescopes. This makes them extremely important tools for studying the galactic center, as well as exoplanets. They can even resolve sunspots on nearby stars. So to understand how we know how close S2 got to Sag A star, we need to understand how these stellar interferometer telescopes work. In the speed of light chapter of the How Fast Is It video book, we covered the Michelson interferometer used to measure minute distances in the lab. Interferometers can measure distances on the order of a few nanometers. Michelson and Morley used it to show that the speed of light was a constant. In order to create light interference, Michelson illuminated the interferometer with fully coherent light. Coherent light has a common frequency and phase. It always produces interference patterns on the far side of a double slit. Fully coherent light, like the kind that lasers create, will produce regions of fully destructive interference. That is, the dark regions have no light falling on them at all. Partially coherent light will produce regions of partially destructive interference, meaning some light falls in the dark regions. And incoherent light will not produce interference patterns at all. We find in nature that waves can start out as incoherent and become partially coherent as they spread out. Watch how these ducks start with a chaotic mix of water waves as they enter the pond. But as the waves move out, they become quite orderly. This is a geometrical effect. The further away one travels from the source, the less significant the distance between the individual wave generators becomes. A point source for starlight would produce coherent light, and at any distance from the source, the light would create interference patterns. But there are no point sources in nature. Stars have a diameter on the sky. An extended thermal light source would start out with incoherent light. But as the light moves away from the source, its coherence increases, just like with the ducks on the pond. It is fascinating to note that incoherent light waves, created by excited atoms in stars 20 billion kilometers apart, can travel for 26,000 years and still carry the remnants of that starting condition. A large enough stellar interferometer can use the visibility dimming of the interference pattern created by the light to detect the original star separation. See how the amount the image fades is greater the further apart the two stars are. The math involved was developed independently by Dutch physicists P. H. van Sittert in 1934 and F. Zernike in 1939. It's known as the van Sittert-Zernike theorem. From antiquity, it was believed that the idea of empty space is a conceptual impossibility. Space is nothing but an abstraction we use to compare different arrangements of the objects. Concerning time, it was believed that there can be no lapse of time without change occurring somewhere. Time is merely a measure of cycles of change within the world. Then, in 1686, Isaac Newton founded classical mechanics on the view that space is real and distinct from objects, and that time is real and passes uniformly without regard to whether anything moves in the world. He spoke of absolute space and absolute time as a stage within which matter existed and moved as time flowed at a constant rate. It was understood that space and time tell matter how to move, but matter has no effect on space and time. The idea that space and time act on matter, but that matter does not act on space and time, troubled Einstein. Noting that light curved in a gravitational field, Einstein proposed that the mass of an object does indeed act on the space and time it exists in. Specifically, he proposed that the presence of matter curves space-time. This led Einstein to his theory of general relativity, which predicts the existence of black holes as objects so massive that light itself cannot escape their gravity. You'll recall explosions at the end of life for stars less than 5 times the mass of the Sun leave behind a white dwarf. In these stars, electron exclusion pressure is enough to counteract the inward force of gravity. Supernova explosions at the end of life of stars more than 5 times the mass of the Sun leave behind a neutron star. In these stars, electron exclusion pressure is insufficient to overcome the force of gravity, but neutron exclusion pressure is. But if a star is greater than 30 times the mass of the Sun, even neutron exclusion pressure won't do the trick. In fact, there is no known force that will counteract the inward force of gravity for such a supernova or hypernova exploding star. According to Albert Einstein's general theory of relativity, the star will collapse into zero volume and infinite density. This is called a singularity. This defines a black hole. It gets its name from the fact that such a singularity would create a gravitational pull that not even light could escape. The object literally becomes invisible. In 1916, Karl Schwarzschild, contemporary of Einstein, solved his equation for the special case of a non-rotating sphere. He found that although the diameter of the singularity is 0, the radius at which light would be captured depends entirely on the mass of the black hole. This is called the Schwarzschild radius, and it defines the event horizon. But it would be the rare black hole that doesn't spin. In 1963, Roy Kerr developed a general solution for spinning black holes. It showed that there is a second region beyond the event horizon that defines a volume around the black hole called the ergosphere. In this region, space itself is dragged around by the black hole's spin. It's called frame dragging. Also in this region, light can enter stable orbits around the black hole. This would produce a photon spherical shell encasing the black hole with the light from all the stars in the universe accumulated over the entire age of the black hole. It would be a sight to see. One of the things all rotating black holes have in common, besides the fact that we can't see them, is that matter flows in via an accretion disk. The exact mechanism is not yet fully understood, but we know that gamma-ray jets shoot out at the poles, carrying a percentage of the falling matter with it at speeds approaching the speed of light. In late 2018, ESO's gravity instrument observed flares of infrared radiation coming from the accretion disk around Sag A star. These flares came from clumps of gas swirling around at about 30% of the speed of light on a circular orbit just outside the event horizon. They indicate that Sag A star is spinning with a full rotation every 11.5 minutes. This makes the 4 million solar mass Sag A star a supermassive Kerr black hole. This new information also enabled calculating the distance from Sag A star's center to its event horizon at around 10 million kilometers, or 15 times the radius of our Sun, and the distance to the photon sphere at around 17 million kilometers. To illustrate how a black hole might look, we'll build Sag A star. Here we are viewing it from the equatorial plane, and the object is rotating in on the left and out on the right. Its center is dark out to the event horizon. This thin ring around the black hole, just outside the event horizon, represents the cross-section of Sag A star's ergosphere, with a shell of orbiting light. What we'd see is the light that leaks out in our direction. The observed flares indicate that Sag A star has the remnants of an accretion disk that is no longer feeding the black hole on a regular basis. The massive amount of light rays emitted from the disk's top face travel up and over the black hole, and light rays emitted from the disk's bottom face travel down and under the black hole. This combination gives us the full image of how the black hole would actually look. There are three classifications for black holes based on their mass: stellar, with masses up to 10 times the mass of our Sun; supermassive, with millions or even billions of times the mass of our Sun; and intermediate, with masses somewhere in between. Sag A star is a supermassive black hole. In March 2018, the Japanese instrument MAXI aboard the International Space Station recorded an extremely strong X-ray outburst. NASA's NICER neutron star instrument, also on the space station, focused on the outburst for days and watched it fade. In addition, the Gaia mission was able to locate the X-ray source companion star and determine its distance at 10,000 light-years. Analysis showed that the X-ray object is a black hole with a mass of around 10 suns. The X-rays are generated as matter from the star feeds the accretion disk around the black hole. Some astronomers calculate that there are as many as 100 million stellar mass black holes like this one in our galaxy. Most of these are invisible to us, and only about a dozen have been identified. For more information on black holes, see the General Relativity Effects segment of the How Fast Is It video book. The number of stars in the Milky Way is very difficult to determine. But based on detailed analysis of star distances, star motions, hydrogen radiation from spiral arms, galaxy rotation curves, and mass, including dark matter, astronomers currently believe that the galaxy has a relatively flat rotating disk, 100 to 120,000 light-years wide and 1,000 light-years deep, with some 100 to 400 billion stars. This image, out of the Spitzer Science Center and the University of Wisconsin, represents an attempt to synthesize over a half-century of work on the galactic disk's structure, based on data obtained from the literature at radio, infrared, and visible light wavelengths. The galactic center itself, with the supermassive black hole that we discussed earlier, is shaped like a bar. Although most parts of the Milky Way Galaxy are relatively uncrowded, roughly 10 million stars are known to orbit within just a single light-year of the galactic center in a region known as the Central Bulge. Recent surveys discovered the two 3-kiloparsec arms, named for their length. They are now generally thought to be associated with gas flow roughly parallel to the central bar. Using infrared images from Spitzer, scientists have discovered that the Milky Way's elegant spiral structure is dominated by just 2 arms wrapping off the ends of the central bar. One is named Scutum Centaurus, and the other is named Perseus. Each of these major arms consists of billions of young and old stars. 3 thinner arms spiral out between the 2 giant arms. These are called Sagittarius, Norma, and the outer arm. These are primarily filled with gas and pockets of star-forming activity. There is also a spur off the Sagittarius arm called the Orion Spur. It's 3,500 light-years across and approximately 10,000 light-years long. We are located on the inner edge, halfway along this spur, around 26,000 light-years from the galactic center. When we fill the space between the arms, we get the full picture. It's interesting to note that the number of stars per unit volume of space in the region between arms is the same as the number in the arms themselves. What distinguishes the arms is that they have a far greater number of younger stars. In fact, all the known H2 star-forming regions in the galaxy exist inside the arms. We don't see any in the area between the arms. If we lay a grid over the galaxy, we can locate some of the stars, nebula, and H2 regions we have seen in this chapter. Actually, all the local neighborhood stars would fit into the red circle I used to locate our solar system. That would be stars like Wolf 359, Altair, Vega, Polaris, Capella, Aldebaran, the Pleiades, and Betelgeuse. They are all with us in the Orion Spur, as is the Orion, Horsehead, Cone, Witch's Head, Veil, and many other nebula. In Sagittarius, we see the Jewel Box star cluster, and the Trifid, Omega, Lagoon, Eagle, and Cat's Paw nebulas, among others. In Perseus, we see the Rosetta, Heart and Soul nebulas, as well as the Crab supernova, to name just a few. In fact, except for the hypervelocity stars and a few of the supernova remnants, everything we have seen in this chapter is within this red circle. As vast an area as we have covered, it is only a fraction of the Milky Way Galaxy. Another point that ought to be covered is that we cannot see through the galactic core into the other side. The core is simply too dense, with stars and gas and dust to penetrate. So this slice of the disk has not been seen or analyzed. But our understanding of spiral galaxies is that they are symmetric. So this picture makes that assumption and fills in the blanks accordingly. Here we see the Sun's orbit around the galactic center. Our orbital speed is approximately 230 kilometers per second, or 143 miles per second. That's fast, but it takes us around 213 million years to complete one orbit around the galactic center. The last time we were in the same place in our orbit, dinosaurs were just starting to appear on the Earth. And we have traveled around 1/10,000th of a revolution since the origin of humans. Here's a look at our solar system's ecliptic plane with respect to the galactic plane. It's just over 60 degrees off. We see that the solar system is quite out of alignment with the galaxy's disk. Earth's 23-degree tilt to the solar plane puts us at an almost 63-degree tilt from the galactic plane. This is why the Milky Way appears at such a strange angle across the night sky. Also, as the Sun orbits the galaxy, it oscillates up and down relative to the plane of the galaxy. It does this approximately 2.7 times each time around. Astronomers estimate that we are currently at around 75 to 100 light years above the galactic plane and moving down. This estimate has us crossing the plane again in approximately 30 million years. Before we leave the galaxy's dusty disk, we'll take a closer look at the dust itself. It's critically important for calculating intrinsic star luminosity, and it's the only galaxy content that we can see to accurately calculate the galaxy's rotation curve. That's star velocities as a function of how far from the center of the galaxy they are. The Milky Way's rotation curve is one of the reasons scientists have proposed the existence of dark matter. The dust is made of thin, highly flattened flakes of graphite and silicate. That's carbon and rock-like minerals, coated with water ice. Each dust flake is roughly the size of the wavelength of blue light, or smaller. The dust is probably formed in the cool outer layers of red giant stars and dispersed in the red giant winds and planetary nebula. The dust absorbs and scatters the light that passes through it. The further the light has to travel, the more of this dust it encounters, and the dimmer it gets. Astronomers call this extinction. Due to this extinction effect, stars in the galactic disk can lose up to half their luminosity every 3,000 light-years. Only the brightest stars can be seen more than 10,000 light-years away. These clouds are best viewed using radio astronomy. This is because gas clouds radiate radio waves, and radio waves pass through dust particles untouched because their wavelength is much larger than the size of these particles. What's more, the hydrogen in these regions emit a spectral line in the radio frequency band, and this spectral line exhibits Doppler shifts, enabling us to measure the cloud's radial velocity relative to us. In this line of sight reading, we see a number of peaks. Each one represents a cloud. Peaks have different frequencies because the clouds have different radial velocities. The maximum peak is from a cloud that's radial velocity is close to its total orbital velocity. The best way to map out the rotation curve for the galaxy's disk is to measure the orbital velocities and distances of gas clouds and star-forming regions across the galaxy. These are the H1, H2, and molecular clouds we covered in our segment on star birth nebula. These are the best objects to analyze for 3 reasons. 1. They trace out the spiral arms. 2. We can see them clearly at great distances using radio astronomy. And 3. There is a good way to calculate their distance for the inner part of the galaxy. So, for clouds closer to the center than we are, we can scan the sky bit by bit and create a map of the rotation velocity and distance for the inner galaxy. This map can then be used to find distances to all the clouds and the stars they contain, as long as they are closer to the center of the galaxy than we are. For clouds further out, there are no tangent points. For these, we have to use weaker methods for determining distance and rotational velocity. We then do a best fit line for the collected data. Here's a graphic superimposed on our galactic curve that indicates the accuracy of methods used to provide the included data points. The vertical lines through each point represent the range of possible velocities for any given distance. Notice that these lines are quite long. Rotation curves give us a measure of a system's mass. And at the outer edge of the disk, the star mass density drops off dramatically. That's why, in the 1970s, everyone expected to see a rotation curve that looked like this. But what we found is that where the velocities were expected to fall off, they remained relatively constant. If our current theory of gravity holds up for galactic distances, then this curve tells us that our model of the Milky Way is missing something. In order for objects far from the center of the galaxy to be moving faster than predicted, there must be significant additional mass far from the galactic center, exerting gravitational pulls on those stars. Not knowing what it is, we call it dark matter, and it extends way into the galaxy's halo. At the turn of the 20th century, astronomer Harlow Shapley, studying a large number of RR Lyra stars inside globular clusters, found that the center of the galaxy was far from the Sun. He mapped 93 globular clusters. They formed a spheroidal shape with their own center, not near the Sun. He concluded that these giant clusters formed the bony frame of the galaxy. This area around the disk is called the galactic halo, or corona. It holds a large number of old stars and 158 globular clusters.
The galactic halo itself has a diameter of at least 600,000 light-years, based on the locations of the globular clusters, although it may extend much further.
In 2007, using 20,000 stars observed by the Sloan Digital Sky Survey, an international team of astronomers discovered that the Milky Way halo is a mix of two distinct components rotating in opposite directions: the outer halo and the inner halo. Then, in 2018, a team of astronomers analyzed 7 million stars from the Gaia mission and found that 30,000 of them were moving counter to the normal Milky Way flow. Star motions and composition profiles indicated that they came from a different galaxy. They call this new galaxy Gaia Enceladus. Using computer models for galaxy collisions, they estimated that it collided with the Milky Way around 10 billion years ago. This is a computer simulation of the merger. Here we see that Gaia Enceladus is now our galaxy's inner halo.
On September 24, 2012, Chandra found evidence that the Milky Way Galaxy is embedded with a large amount of hot gas in the halo. Counting this vast amount of gas, the mass of the halo is estimated to equal the mass of the stars in the galaxy.
But as massive as it is, the amount of matter in this hot gas is not nearly enough to explain the galaxy's rotation curve. Dark matter, or a new theory of gravity, is still needed. In 2018, using both Hubble and Gaia data on globular cluster sizes and velocities, the mass of our galaxy was estimated to be at least 1.5 trillion times the mass of our Sun. This is more than previous estimates and indicates that the Milky Way is among the universe's larger galaxies.
Let's take a closer look at how an image like this is created. From orbit, we point the camera at the center of the galaxy and then turn it 180 degrees to face away from the center. We're now looking through the plane of the galaxy, away from the center. Then we scan the camera clockwise, taking hundreds of pictures along the way. We continue the rotation through the center and all the way back to the starting point. Note that the stars on the right edge of the image, taken at the end of the rotation, are adjacent to the stars on the left edge of the image, taken at the beginning. In other words, the entire right side of the image borders on the left. Now we rotate the camera up a bit and repeat the process. We do this over and over until the entire northern sky is covered. The last shot is taken with the camera pointing straight up, perpendicular to the galactic plane. We then repeat the process for the southern sky, and we have the entire picture. Once we have all the pictures covering the spherical surface of the sky all around us, we map it to a flat surface. There are a number of ways to do this. Astronomers use the elliptical projection method because it maintains the relative size and distance between celestial objects. You may have seen maps of the Earth that use this technique. We started with an image of the Milky Way constructed within the galaxy. Whenever you see any picture of the whole Milky Way from outside the galaxy, remember that it is an artist's drawing. The size of the galaxy is so large that the distance one must travel to see it all is way too far. Here's what I mean. If we assume that our field of view is 140 degrees, we can use trigonometry to find the distance to a point where such a picture could be taken. That point is approximately 301,000 trillion kilometers, or 187,000 trillion miles from the Sun's current location. Voyager 1 left on its journey in 1977 and is traveling at 61,000 kilometers per hour, or 38,000 miles per hour. It has already gone 21.2 billion kilometers, or 13.2 billion miles. If we aim it at the photographic point, at its current velocity, Voyager won't reach this point for another 562 million years.
In our chapter on the Milky Way, we studied the nearby stars where parallax told us how far away they were. We developed the HR diagram as a way to calculate luminosity based on temperature and spectral analysis. We covered key standard candles such as Cepheid and RR Lyra variables, as well as Type 1a supernova. And we examined star clusters, planetary nebula, and emission nebula for their beauty and value as standard candles. This distance ladder took us all the way across the galaxy. In our next chapter, we'll use all these techniques to move out into intergalactic space.